everyone, my name is Hakim, and today, together with Wenhan, we'll be discussing the derivation of Maxwell's thermodynamic relations. There are 4 of these relations, with the alphabets representing the respective quantities on the right. To do so, we'll need to use the partial derivative rule, which states that dfxy equals to del f del x keeping y constant dx plus del f del y keeping x constant dy. Let's begin with the first relation, which states that del t del v keeping s constant equals to negative del p del s keeping v constant. By the first law of thermodynamics, we know that U equals to Q minus W. This implies that du equals to dq minus dw. If we substitute dq equals to tds and dw equals to p dv, we get the relation du equals to tds minus p dv, which we will label as equation 1 and will be used for the derivation of the other 3 equations. By the partial derivative rule, we know that du equals to del u del s keeping v constant ds plus del u del v keeping s constant dv. Comparing coefficients, we get t equals to del u del s keeping v constant, which we label as equation 2, and p equals to negative del u del v keeping s constant, which we label equation 3. Taking the partial derivative with respect to v keeping x constant on both sides of equation 2, we get del t del v keeping s constant equal to del v of del u del s keeping v constant keeping s constant, which equals to del square u over del v del s. Taking partial derivative with respect to s keeping v constant on both sides of equation 3, we get del p del s keeping v constant equals to del s of del p del v keeping s constant keeping v constant, which equals to del square u del v del s. Therefore, we'll get the equation del t over del v keeping s constant equal to negative del p over del s keeping v constant, which is what we set out to prove. The other relations are shown here. Thank you. This has been the derivation of Maxwell's 4 thermodynamic relations with Hakim and Wenhan.